Encapsulation and Decapsulation. In this lesson, we're going to talk about encapsulation and decapsulation. Encapsulation is the process of putting headers and sometimes trailers around some of our data. Think about it like this. You just finished writing a letter to your grandma, and now you want to send it to her. Well, to do that, you need to put it in an envelope. Now, when you put the letter in the envelope, you're actually encapsulating it. Now, once your grandma gets that envelope, she wants to be able to read it, and so she has to take the letter out of the envelope in order for her to read it. This process is known as decapsulation because we're removing the encapsulation that was applied earlier. Now, I know this is a silly example, but that's exactly what happens as we send data on our networks. It's continually being encapsulated and decapsulated as it moves up or down the layers of the OSI model. If we move down the OSI layers from 7 to 1, we encapsulate our data. If we move upward from layer 1 up to 7, we decapsulate our data. So let's take a closer look at how this works in the real world. In the OSI model, we use protocol data units, or PDUs, to transmit our data. A protocol data unit is just a single unit of information transmitted within a computer network. In the OSI model, they are simply called L, the layer number, and PDU. For example, L7 PDU is a layer 7 PDU. This type of terminology can be used for every single layer we have, but we also have special names for the PDUs when we reach layers 1, 2, 3, and 4. For layer 1, we call them bits. For layer 2, we call them frames. For layer 3, we call it packets, and layer 4, we call it segments if we're using TCP, or datagrams if we're using UDP. Now, as a user creates data and they want to send it over a network, they're going to enter it into an application at the application layer, layer 7. This data then has a layer 7 header added that contains metadata with the parameters that are agreed upon by the specific application. So if you're using HTTP or you're using FTP, that's going to have specific metadata for that type of data. Then that information is going to be passed down to layer 6, where it's going to encapsulate the layer 7 header and data together and then add its own layer 6 header, which contains its own metadata with information about the presentation or encryption formats being used. Next, it's going to pass this down to layer 5, where it encapsulates the layer 6 header and the layer 6 data, and then it's going to add its own layer 5 header based on the metadata about the session. As you can see, it's like taking a letter, or in this case data, wrapping it in an envelope, and then writing some information on that envelope. That's our header. When we hand it to the next person, they're going to put it in an envelope and write their own metadata on the outside of the envelope and then pass it to the next person. And we keep doing this as we go down the layers, all the way down to layer 1. Now, the headers added at layers 4, 3, 2, and 1 are very specific, and they actually help ensure the message is going to reach its final destination. So let's take a look at the header that's added at layer 4, the transport layer. Now, if you remember, the transport layer uses different protocols like TCP or UDP. The TCP header has 10 mandatory fields, totaling 20 bytes of information. This includes our source port, the destination port, the sequence number, the acknowledgement number, the TCP data offset, the reserved data, which is currently always going to be set to 0 because it's not really used, the control flags, the window size, the TCP checksum, the urgent pointer, and the MTCP optional data. Now, you don't need to know all of these fields in depth, but there are a couple that are pretty important. For example, the source and destination ports are pretty important to understand because this helps determine where the information is being sent from and where it's being sent to, and allows it to go through a firewall by going to the right ports. Also, the sequence number and acknowledgement numbers are going to be used to ensure all the data is properly received by the destination when it's sent by the original transmitter. So this is also important when you're using TCP. Another important concept in the TCP header is the control flags. There are 6 control flags that are used to manage data flow before, during, and to stop the data communication when you're finished. You should already be familiar with the 3-way handshake. That uses the SYN packet sent by the client, the SYN-ACK packet that's sent by the server, and the ACK packet that the client sends back to the server at the end. These packets are sent using the TCP flags of SYN or ACK inside your TCP header. Now, in addition to these SYN and ACK flags, there's also 4 others: FIN, reset, push, and urgent. First, we have the SYN flag, or synchronization flag. This is by far the most well-known flag in TCP communications because it's used to synchronize the connection during the 3-way handshake. Next, we have the ACK, or acknowledgement flag. This is also used during the 3-way handshake, But in addition to that, we use it to acknowledge the successful receipt of all the packets during the communication. The fin or finish packet is used to tear down the virtual connection created by the three-way handshake and the SYN flag. The fin flag always appears when the last packets are exchanged between a client and a server and the host is now ready to shut down that connection. Next, we have the RST flag or reset flag. This is going to be used when a client or server receives a packet that it was not expecting during the current connection. For example, if you tried to establish a connection with a server that didn't want to accept any new connections, it could send back an RST or reset flag to inform your client that it's not accepting connections and automatically reject your request. The next one we have is a PSH flag or push. Now, a push flag is used to ensure the data is given priority and is processed at the sending or receiving ends. Most often, this flag is added to a packet at the beginning or end of a data transfer. The final flag we have is URG, or the urgent flag. The urgent flag is like the push flag, and it identifies incoming data as urgent. Now, the main difference here between push and urgent is that push is used by the sender to indicate data with a higher priority level. Now, urgent, on the other hand, is sent to tell the recipient to process it immediately and ignore anything else that's in the queue. With urgent, this could lead to packets violating the first in, first out priority order, so it needs to be used only by particular applications when necessary. Now, if you're using UDP instead of TCP, you're going to be using the user datagram protocol. Now, when we look at the user datagram protocol header, this is another transport layer or layer 4 header that's going to be used in our networks. Remember, UDP is unreliable and it's a connectionless protocol, so its header is significantly smaller than TCP. With UDP, we only have an 8-byte header instead of the 20-byte header used in TCP. UDP only has 4 fields that are used: the source port, the destination port, the length, and the checksum. The source and destination ports are just like the ones used in TCP. They dictate where the data is coming from and where it's going to. The length is used to indicate how many bytes the total UDP packet is, including the header and its data. The checksum is not a mandatory field, but instead it can be used to provide some validation that the UDP data being sent was actually received with some level of integrity. Next, let's move down to layer 3, the network layer. As we move down another layer, we're going to again encapsulate the data and add a header. This time, we're going to add the IP or Internet Protocol header. The IP header is going to contain several fields, including the IP version, the length of the IP header, the type of service, which was defined by the standard but never really used, the total length of the packet and header, the identifier, the flags, the fragmented offset, the time to live, the protocol, the header checksum, the source IP, the destination IP, and the options and padding. Now, as we continue down the layers, we're going to reach layer 2, the data link layer. And this is going to encapsulate the data by adding an Ethernet header. Now, this header features just a few things, including a destination MAC address, the source MAC address, the ether type field, and an optional VLAN tag using either IEEE 802.1q or IEEE 802.1ad. We're going to talk more about VLANs in a separate video though, because it's an important concept. So let's talk about a MAC address. A MAC address is a physical address that's used to identify a network card on your local area network. This allows our source to find our destination by using this type of layer 2 addressing. This is what's processed by switches in your network. Now, the ether type field is used to indicate which protocol is encapsulated in the payload of that frame. So, if you're using IPv4 or IPv6, this can be indicated here using the ether type field. Now, in addition to the Ethernet header, a frame being sent at layer 2 will also contain a payload. In Ethernet, the minimum payload is 42 bytes if VLANs are being used and 46 bytes if no VLANs are being used. Now, when you're trying to send a payload, there is a maximum size to this, known as an MTU, or maximum transmission unit. When we talk about payloads, this is the data we're trying to send across the network. By default, Ethernet uses an MTU of 1500 bytes as its maximum size. Now, if you have a payload that's larger than 1500 bytes, then you need to allow for what's known as a jumbo frame. This just means the frame is going to be larger than 1500 bytes. To configure this on your switch, you're going to reconfigure your MTU size, or your maximum transmission unit size, to larger than 1500 bytes. Alright, that was a ton of information we just covered, but let's review a couple of main concepts here. First, remember, as data moves from layer 7 to layer 1, we are going to encapsulate that data. So, as we move down the OSI layers, we're going to encapsulate that data and add a header at each of those layers. At layer 4, we're going to add our source and destination ports. At layer 3, we add our source and destination IP addresses. At layer 2, we add our source and destination MAC addresses. Now, once we get to layer 1, we're simply transmitting our layer 2 frames as a series of 1s and 0s over the medium. When it's received by the next device, for example a switch, it's going to put the frames back together from the electrical, optical, or radio frequency signals that it received over layer 1. Now, it's going to decapsulate the layer 2 information by reading the Ethernet header. If the destination MAC is on one of the switch ports, it's going to send the message to it. If not, it's going to forward it to its default gateway, which is a router. This router then decapsulates the data to layer 3, and it reads the destination IP address. If it's on its network, it's going to forward the data to that device. If not, it's going to re-encapsulate the data and send it out its default gateway. And then this process will continue until the final destination or host is found. Now, once that host is found, it's going to keep decapsulating that information all the way back up to layer 7, where its application can read and understand the underlying data. Now, we're going to cover a lot more about how this data transfer happens when we talk about switches and routers later in this course. But for now, this is the basics you need to understand.